So this section is on momentum. Momentum is represented by the letter P, and it's equal to mass times velocity. Because velocity is a vector, and mass is a scalar times a vector is a vector, or just a number times a vector is a vector, so momentum is a vector. Hopefully you have some sense of what momentum is. If we're talking in one dimension, we can just remove the vector notation and say P is equal to mass times velocity, right? And so an elephant moving at 5 meters per second, right, has more momentum than a human moving at 5 meters per second because the elephant has more mass. Momentum shows up in a lot of things, in collisions and in sports and things like that. So we can give an example. A car traveling at 20 meters per second has mass 1,000 kilograms. What is its momentum? Now this is kind of a one-dimensional problem. I haven't got a direction in here, even though momentum is a vector, but when I write 20 meters per second, I assume that's going in one direction, so I'll say P is equal to mass times velocity, right? This is a one-dimensional problem, maybe along the x-axis, and that's equal to 1,000 kilograms times 20 meters per second, or 20,000 kilogram meters per second. So the units for momentum are kilograms times meters per second, right? Now when we were doing newtons, when we're doing force, we said a kilogram meter per second squared is a newton. There's really no name for this one. So we either write as a kilogram meter per second, or sometimes we call it a Newton second, because a Newton is a kilogram meter per second squared times a second gives you a kilogram meter per second. The total momentum is just the sum of the momenta for a bunch of different particles. I could have a collection of birds flying along in different directions, or 2 or 3 cars driving down the highway. The total momentum, this could be, 3 defensive linemen running after the quarterback or running after a running back or something like that. If I add up the mass times velocity for 1 plus the mass times velocity for 2 plus the mass times velocity for 3, I get the total momentum. And so, if this is P1 and this is P2 and this, right, these are all vectors, is P3, all right, then P tot is P1 plus P2, right? I drew a P1 plus P2 So the total momentum for a system is just the vector sum of each of the individual momenta for the system. And so if I want to add up the momentum for several different objects, like for example 3 cars going down the highway, or 3 birds flying through the sky, or some number of football players, defensive linemen running forward or something like that, I just add them as vectors. Right? And so if this is my P1, this bird's flying this way, this is my P2, this bird's flying this way, this is my P3, this bird's flying this way, or this player's running this way, or this car's going this way, or something like that. If I want to add them up, I just add them up as vectors. Here's my P tot, it's just P1 plus P2 plus P3. Again, when I'm adding vectors, I just take the first vector, start the second vector at the tip of the first one, and then I start the third one at the tip of the second one, and then to draw my sum, I just draw a line connecting the beginning of my first vector with the end of my last vector, and that is my P tote. And so momentum just adds like a vector. And so if I have some system that I'm watching, I can just sum up the vectors in that system and watch the total momentum of my system by watching my P tote vector. So that's how we add vectors graphically. Suppose we want to add vectors algebraically. We go back to our old method of adding vectors by components. If we have the vector P tote equals P1 plus P2, right? What we do is we break our vectors into components and we add up the components. So I would say, P tote x is equal to P1x plus P2x, right? The two x components, and that's equal to this one is 100 kilogram meters per second times the cosine of 45 degrees plus this one is 200 kilogram meters per second times the cosine, we'll call that 30 degrees. And so that gives me a P tote x, right? The x component of my P tote vector of 100 kilogram meters per second times the cosine of 45, which is like 71 kilogram meters per second, plus 200 kilogram meters per second times the cosine of 30, which is like 173 kilogram meters per second. So this is like 244 kilogram meters per second, right? Similarly, P tote y is equal to P1y plus P2y, and that's equal to the vertical components, which is 100 kilogram meters per second times the sine of 45 degrees plus 200 kilogram meters per second times the sine of 30 degrees, and that's equal to, like, this one's a 71 and this is 100, so 171 kilogram meters per second. And so to get P tote y, to get P tote, I use the Pythagorean theorem, right? And that's the square root of P tote x squared plus P tote y squared. And for that I get uh, 298 kilogram meters per second, right? And to get the direction, I say theta is equal to tan inverse of P tote y over P tote x, right? And so that's uh, 35 degrees. So here's number one in your book, just an example. You have a particle of 5 kilograms moving at 4 meters per second and a particle of 3 kilograms moving at 8 meters per second. What's the total momentum? Well, these guys are moving in one dimension, so I can just do P tote is equal to P1 plus P2, because they're all in one line. I don't have to worry about components. And that's 5 kilograms times 4 meters per second, plus 3 kilograms times 8 meters per second. And that's equal to 20 kilogram meters per second, plus 24 kilogram meters per second, or 44 kilogram meters per second. So that's my total momentum. So if I do another one of those, I can say I've got a particle here that's 9 kilograms traveling at 4 meters per second. And a particle over here that's 6 kilograms traveling at 8 meters per second. Right. And so P tote is P1 plus P2, and that's 9 kilograms times 4 meters per second. And the other one is 6 kilograms times 8 meters per second. And the catch here is what? These are supposed to be vectors, and so even in one dimension I have to specify direction. This guy's going in the negative direction. I have to put a minus sign there. And so this is 36 kilogram meters per second minus 48 kilogram meters per second, or minus 12 kilogram meters per second is my P tote. In other words, the total momentum of this system is moving to the left, not to the right. So let's do another example. Now I've got a particle moving downward and a particle moving up and to the right, and this one is moving right at an angle of 30 degrees relative to the horizontal, and this one's moving straight down. And we want to know, what is P tote X and P tote Y, right? We want to combine to find the total momentum of this system in the vertical direction and in the horizontal direction, right? And so if we look at this particle, if we call this one particle 1 and particle 2, we can say P1X is equal to, well, it's got no component in the X direction, so it's just 0, right? P1Y, its velocity is in the Y direction, and so it's it's 5 kilograms times 4 meters per second, but the velocity is in the negative direction, so I have to be careful to put a negative sign on there. And so P1Y is equal to negative 20 kilogram meters per second, right? Similarly, I can find P2X, right? If I want the components of this guy, my X component is going to look like this, right? And my Y component is going to look like this. This is P2Y, and this is P2X, right? This is just P2 cosine 30 degrees, which is just the mass, which is 10 kilograms times 4 meters per second, right? That's the momentum. And then I have to take the cosine of 30 times 0.866, right? And so this is, about 34.6 kilogram meters per second, right? In the momentum in the X direction, and then P2Y is equal to P2 sine of 30 degrees, which is 10 kilograms times 4 meters per second times 0.5, because the sine of 30 degrees is 0.5. This is 20 kilogram meters per second. So we can see that P tot, the total momentum, x, is equal to P1x plus P2x, but P1x is just 0, so 0 plus P2x, 34.6 kilogram meters per second, or just 34.6 kilogram meters per second. Similarly, P tot y is equal to P1y plus P2y. That's equal to minus 20 kilogram meters per second plus 20 kilogram meters per second, or just 0. So the total momentum is just the x component. The total momentum has no y component because the upward component of this guy cancels the downward component from this guy, and I just get a momentum for my total of 34.6 kilogram meters per second to the right as a result of the x component for that guy. So we can talk about Newton's second law with momentum. If you remember, Newton's second law is F equals ma, right? Or if we wanted to write it in a little more complete way, we would say the sum of the forces is equal to the mass times the acceleration, right? Well, acceleration is just the change in velocity divided by the change in time. And so what we could say is the sum of the forces, right, is equal to the mass times the change in velocity divided by the change in time, right? But mass times the change in velocity is just mass times velocity final minus velocity initial, right? But we can rewrite that as mass times velocity final minus mass times velocity initial, right? But mass times velocity final, that's just P final, right? Because mass times velocity is momentum. Similarly, mass times velocity initial is P initial. And so this is just the change in momentum. So mass times change in velocity is change in momentum, and so we can say the sum of the forces, going back to this equation, is equal to the change in momentum divided by the change in time. That is, the change in momentum here is just delta P, right, divided by the change in time. And so this is the momentum way of writing Newton's second law, and it's really the way Newton said it. Newton said the sum of the forces is equal to the change in momentum over the change in time, or the rate of change of the momentum. So now let's talk about conservation of momentum, right? This is Newton's second law in terms of momentum, and this is just, you know, the sum of external forces on the system. Obviously, we don't worry about internal forces, like the forces that are holding the wheels on the car or anything like that. It's just forces from the outside. And this is the momentum. And so we could be talking about like an individual particle and looking at how the momentum of the individual particle, an individual particle, changes with respect to the forces acting on it. This could be a block on a plane, or this could be, you know, a car on the highway or something like that. But this could also be the total momentum of a system. This could be two cars, for example. And what are the external forces on the two cars? And usually, when we use Newton's second law with regard to momentum, we're talking about some kind of conservations of momentum problem. And so let me give an example of that. Consider a system with no external forces, or at least one where the external forces are balanced so that the sum of the external forces is 0. So for example, we could consider two ice skaters skating on ice where it's frictionless. And you might say, well, the skater has a a normal force and gravity acting on them, but those two cancel. Those two are in opposite directions and they cancel. And so the net force on an ice skater sitting on a frictionless surface is 0. And so if we consider two ice skaters and they're colliding or something like that, what we get, or even just one ice skater, we get the change in momentum over the change in time is equal to 0. Well, as long as the time isn't 0, which would be silly if it was, because then we'd be just talking about the same instant, right? As long as this term isn't 0, then this means that the change in momentum is equal to 0 for our system. And so if it's a couple of skaters, we could say, you know, P tote final minus P tote initial is equal to 0. Right? And what that says is that P tote final is equal to P tote initial. In other words, in a system with no external forces, momentum is conserved. So let's consider an example where we can talk about this momentum conservation. We're going to pick a system where we have ice skaters, right? And the surface is frictionless. Right, and so Mary, with an initial velocity of 5 meters per second to the right, is skating towards Bob, who looks a little nervous, and is at rest, right? Mary's mass is 50 kilograms, Bob's mass is 70 kilograms. And so she skates up to him and leaps, and he catches her, and they skate off together, and we want to know what the final speed is. And all we know is that the surface is frictionless, which tells us that momentum is conserved. So what we can say is P tote initial is equal to P tote final. That's really all we know. Let me make a smaller f out of that and a smaller I. And so our initial momentum is P Mary initial plus P Bob initial. And we're saying that's equal to P Mary final plus P Bob final. Right, well, the initial momentum of Mary is just mass of Mary times velocity of Mary initial plus the mass of Bob times V Bob initial. And that's equal to the mass of Mary times V Mary final plus the mass of Bob times V Bob final. And so we can say a few things. First of all, Bob's initial velocity is 0, and so this term just goes away. Right? Second of all, we can see up here that V Mary final is equal to V Bob final. That is to say, if he catches her, they're traveling at the same speed, and so we just call those two things V final. And so what this equation now says is, look, mass of Mary times V Mary initial is equal to, let me just write it this way, mass of Mary times V final plus mass of Bob times V final, or that's just the mass of Mary plus the mass of Bob times V final. Well, if we want to solve this for V final, we can just say, look, V final is equal to, so this is equal to that, and so V final is just mass of Mary times V Mary initial over what's in parentheses here. Mass of Mary plus the mass of Bob. Well, what is that? That's the mass of Mary is 50 kilograms times 5 meters per second divided by 50 kilograms plus 70 kilograms. And so this is 250 kilogram meters per second divided by 120 kilograms, right? This is about 2.08 meters per second. That's the speed they travel off with.